Welcome everybody. One of the things we learned from all this Zoom time is that it's important from time to time just to get up and stretch our legs. We got the chance for that. Thank you for that, Robin. So the next speaker is Robin Evans from Oxford University, Associate Professor in Statistics and a Fellow at Jesus College. He will be talking about parameterizing and simulating from causal models. We are a little asynchronized with time, but I will keep track, so we have 30 minutes for talk and questions. So Robin, the virtual floor is yours, please.
Okay, thank you. I'll just interrupt the screen sharing, shall I?
Yeah.
Okay. Right, can you all see this?
It's perfect, it's perfect.
Excellent. Well, thank you very much for the invitation to speak. Thank you to Thomas Richardson, who I think originally invited me. I'm guessing he's not on the call, given that he's in Seattle and it's rather in the middle of the night there. So I'm going to talk today about a paper that I've written with my colleague Vanessa Diedlers, who's based in Bremen, and it's about parameterizing and simulating from causal models using techniques for marginal models. Okay, so I'm going to outline a problem in causal inference. It's related to marginal structural models, actually, that Vincent was talking about. And then we're going to propose a solution. Then I'll develop some theory and show you some simulations to prove that it actually really does work. So what's the problem? So this is a pretty simple causal model. It's a two-step dynamic treatment model. And the idea here is that at the time one, patients are, say, randomly assigned a treatment, which we're going to call capital A. And then we observe from them some sort of intermediate outcome based on this is presumed to depend upon the treatment they're given. And then on the basis of both the first treatment and this intermediate outcome, they are then given a second dose, which is now dependent on those two factors, but other than that is randomized. And then on the basis of all three of those things, they'll have a final outcome, which we're going to call Y. And of course, because these outcomes are measured on the same patient, we're going to expect that these two things will have some unobserved confounders affecting them both. So a sort of standard causal question we might want to ask is, suppose that we fixed both the treatments in advance to be big A has to be little a and big B has to be little b, then what would happen to the distribution of Y? So we're trying to do an intervention where we sever these two edges into B and see what would happen to the distribution of Y. So we want this distribution, which I'm going to denote with the do notation. So it's the distribution of Y given that we intervene to set A is equal to little a and B is equal to little b. So it's been very well known for a long time how to identify this, first due to Robbins. So we just write out the factorization according to the causal order. And then because A and B don't have any unobserved parents, we can just truncate those terms to replace them with ones. And we get magically the distribution of the remaining variables, Z and Y, after intervening to fix A and B. And then if I want this distribution only over Y, I just sum out Z or integrate out Z. Great. So we know how to identify this causal distribution. And this is, in fact, how lots of inference is done in marginal structural models, which is effectively what this is. But this leaves various other questions open. So the first question you might want to know is, how can we describe the whole joint distribution P given some particular parametric model for this part of it? And it's sort of not obvious how you would do that, because this is a marginal of a strange object where you've divided by a conditional part. So that's the sort of first problem. Second question is, how can you simulate from this distribution P subject to this having the particular parametric form you're interested in? And that's also going to be quite hard, as we'll see. And then the third question, sort of even more ambitious in a sense, is how could we fit a parametric model for this thing using data from P with likelihood-based methods? And yeah, so I'll have a quote a little bit later on to show that this is not a trivial thing to do at all. Okay, so those are the three problems. So just to think about the obstacles that stand in the way of doing this. So from the paper that we obtained this model, which was written by Vanessa and a student of hers about 9 years ago, they note that actually simulating from this model such that P of Y given do A and B doesn't depend on A at all is actually very difficult. And they only manage to do it in the case where there's no direct effect of Z on Y. So it's a special case they're able to do it in. As far as the likelihood aspect goes, so in one of the original papers on marginal structural models by Robbins, he says of these models, the difficulty in performing likelihood-based inference is because the likelihood is a computational nightmare. So it's clearly a difficult problem to evaluate what the likelihood of a model like this is when you're specifying that particular structural part, the Y given do A and B. Okay, so what's our solution to this problem? So the main thing is to think about the causal distribution. So this thing I derived earlier, which was the product of these two conditionals. And remember, this is the distribution of Y and Z after we've intervened on A and B. And it turns out it's much easier if we just try and model this directly. And then we're going to use techniques from marginal modeling. So we're going to suppose that we've got a marginal model for the margin of this over Y, which, if you remember, that was the quantity that we're interested in. So we expect to have a model for that. And we're going to assume that we also have a model for the other margin, i.e. the margin over Z, given A and B. And you can see that, in fact, if I sum this quantity over Y, this term will just disappear, and I'll just be left with the ordinary conditional of Z given only A. So this is also a nice thing to have. So now that's good. So we know two parts of this interventional distribution, but we need something to tie those two margins together. So we need some kind of dependence measure which will join them together given the margins. So the sort of canonical example of a dependence measure is the conditional odds ratio for if Z and Y are discrete. And that is precisely what you need to complete a distribution given the two margins if you have the margins of Z and Y separately given A and B. Okay, and then we'll see there are other examples you can use in the continuous case. Okay, so once I've got these three things, so these two margins here and this, then any other information about P star is now redundant because I know everything about it already. Okay, so the solution to our problem, the first problem is to specify separate parametric models for these three quantities. So first of all, what I call the past, which is everything that's causally prior to Y. Then a model for the causal quantity of interest. And then finally, some dependence measure within the causal distribution. So after I've done an intervention on, in this case, A and B. And if I have those three things, then I will have a nice smooth, assuming all the three models, these three models are smooth, and presuming I choose this dependence parameter carefully, it will also be that these three quantities are variation independent. And sort of even more than that, you can get any distribution over those four variables with models of these three things. So we call this a frugal parameterization. So frugal in the sense that there's no redundancy, but you can get any distribution provided you specify these things appropriately. And the nice thing is that we can use methods from marginal modeling to reconstruct things like the log likelihood for P star. And then we just add on terms that relate to P and P star, which we'll specify parametrically as well. Okay, so I'd sort of brushed over this idea of the question of what phi star should be. And that's because obviously it depends on the particular kind of data that you have. But as I say, in the discrete case, you can use conditional odds ratios, and they're very nicely behaved. If in the multivariate Gaussian case, you can use a partial correlation. That's sort of obvious dependence measure. And then in the general continuous case, you can use a Copula model. And Copula models are really nice because they'll give you a closed form likelihood, and they're very easy to simulate from. So they're going to solve both problems 2 and 3 for us as well. Yes, exactly what I just said. Okay, so what are the main results? So the setup we're generally going to consider is where we've got 3 or maybe 4 different groups of variables. So we have treatment and effect modifiers X. So in our previous example, that was A and B. We have outcomes Y. So in our previous example, that was just Y. And then we have other variables that need to be marginalized, which we're going to call Z. And again, in our previous example, that was also called Z. And then you can also include covariates separately if you like, but really you can just have them be part of X, and it will work just as well. So this is a sort of cartoon of what's necessary. All you really need is that X, C, and Z are causally prior to Y. And so before, for example, we had one treatment was causally prior to Z, and the second treatment was causally subsequent to Z, and that's also fine. So there's, although I've drawn these arrows as though there is a causal order, there doesn't actually have to be an explicit one. So what's our main result? So the theorem is that if you have an outcome Y and some causally prior variables C, Z, and X, then you can smoothly parameterize, so you get a really nice map to the joint distribution with models for these three things. So that's, again, the past, the things that come before Y, the causal quantity you actually want to model, and this dependence measure, which joins together Z given Cx and Y given Cx. So I'm just labeling these here. And you notice here I'm saying this has to be a quantity that's what we call cognate, which is something I'll define in a second. So it can be much more general than just P of Y given do X and C. So we'll see there are other things you can parameterize in exactly the same way as we have done the model that I gave as an example. Additionally, any of these variables can be vectors, right? So we saw before that X was equal to A and B. And there's nothing to stop you from having vector values for C, for Z, and for Y as well. So it's actually much more flexible than this theorem might make it sound. So this gives us exactly what we want, right? We've got a coherent joint distribution, P, which we can construct, and we're dividing it into three pieces, one of which is exactly what we want to model. So just to give a sketch of the algorithm that sort of is essentially the proof of this. So what do? Well, first of all, we use this piece of the past to construct this marginal piece that's in the intervened world. So in our example, that was just P of Z given A, but in general, it might be just P of Z, for example. And then we're going to combine the piece that we're interested in and this marginal that we've constructed with the dependence measure, and then we'll get from that, by whatever method is appropriate, the joint distribution of Y and Z, given the treatments and the covariates, under the causal models. That's why there's a star on this. So in the case where this is a conditional odds ratio, you just use iterative proportional fitting to get your margins to be what you want them to be. If it's a copula, then you can use the inverse CDFs of these guys to scale the distribution to be what you want. Okay, and then of course, we're actually interested in P, not P star. So then we should compute the ratio of the past, which we know, and this quantity that we computed in one, and then multiply that by this quantity here, and that will give us P. So we've got a nice closed form way of computing P, provided that we have a way of computing this, which we all assume that we do. So certainly for copulas and for odds ratios, it will all work fine. So what's this business of something being cognate to a conditional distribution? So just for clarity, I'm going to stop using C now. So it's just going to be Z, X, and Y. So we say that P star of Y given X is cognate to P of Y given X if there's some kernel, which is just a word for a conditional conditional distribution, such that when you take the sort of inner product with this conditional, you get P star. So, okay, that seems quite abstract. Let's have some examples. So reassuringly, P of y given x is cognate to itself. Right, so if I choose this conditional distribution, then I will get back just P of y given x. It's good. P of y given do x is also cognate to P of y given x, because if I just put in the margin for z, assuming that causal ordering I showed you in the cartoon, then this is just the G formula which will recover P of y given do x. But you can also have other things, other more interesting distributions. So this is a nice example, I think. So this is looking at the counterfactual. So this is the distribution if you intervene to set x to be little x, but in a population where actually x was something else, it was equal to x prime. So to get that, we just obtain this. So again, this looks like it's an expectation, therefore it's different, but actually, of course, it's exactly the same as integrating over the conditional probability. And I just integrate it with respect to P of z given that particular value for x being x prime. And this means that, in fact, we don't have to just parameterize the average treatment effect, which is effectively what we're doing when we use this quantity. We could have something like the effect of treatment on the treated in our model as well. So our theorem is actually very, very general. Okay. So how do we do simulation? So we know we're going to assume that we can simulate from P star, and that's plausible because we know that Copula models are very easy to simulate from, and also in the discrete case, simulation is essentially trivial, right? You just have the probabilities, so you can do it. And then what we're going to do is use rejection sampling to get back to P, to samples from P. So for each of the triples that we can sample from P star, we consider this ratio of the distribution of P star divided by the distribution of P. And in principle, we should have to put yi in here. But actually, if you go back and check, you can see that the conditional for P of y given zx is the same as the conditional for P star of y given zx. So that part just cancels out. So this is the only thing I need to evaluate in order to perform rejection sampling. And if I do that, then the samples I don't reject will be exactly from P. So note that because we're only, our rejection only depends upon the values in the x and z margins, that means it won't affect this distribution. So that means that the quantity we're interested in will be preserved. So if you apply whatever operation it is that you need to get to P star of y given x, it will be just as you expect within the samples from P. Okay, so just in case you're not familiar with rejection sampling, this is a little cartoon which explains it. So suppose you want to sample from this red density, but it's obviously far too complicated to sample from directly. You could pick another density which is much simpler. So in this case, it's Gaussian, and then you scale it so that it's always above. Interesting. You scale it so it's always above the curve you actually want to sample from, and then sample from this easy to sample density. And here I've scaled each of the samples with a random uniform so that it lies between the curve and the x-axis. And then all you have to do is accept the samples that lie beneath the red curve, and you can sort of see immediately that what you're getting is a sample from the red curve by doing that. So that's very nice. It gives you exact samples from the difficult to sample from distribution. Okay, so here's a specific example that's related to the running example that we've been looking at. So we're going to consider this, again, this two-step dynamic model from the paper by Havercroft and Diedles. And we're going to pick A and B to be binary treatments. So initially in P star, we'll pick them to be independent, and their value is 1 with probability a half. So they're Bernoulli a half random variables. And then we're going to choose Z to have an exponential distribution. And we use, and I'm using the log link here. So the rate parameter for Z is e to the a, and therefore its mean is e to the minus a. And then I'm going to choose a normal distribution for y given intervention on a and b. So its mean is has parameters -1 for the intercept, a half for a and b, and then 0 for the interaction parameter. And I'll choose the variance to be 1. And then to join y and z, I'm going to use a Gaussian copula for simplicity. And I pick the correlation parameter to be half plus, so tan, hyperbolic tan of a half plus a over 4, which is the same as this function here. Okay, and that's using this function is just a way of keeping the correlation between -1 and 1. There's nothing particularly clever about that. Okay, so now I've got my distribution P star that I've constructed, and I can sample from it directly because I just take a bunch of samples from this Gaussian copula model after having sampled A and B, and then I scale them to have the correct marginals. And then for my rejection sampling step, I just need to change the distribution of B conditional on A and Z, and I'll arbitrarily pick it to be Bernoulli, and we'll use a logistic regression. So the parameters are the intercept is 0, and the coefficients of A and Z are both a half. Okay, and we can simulate very quickly from this model, in fact, because rejection sampling is very efficient in small dimensions. So I'll take a sample size of 1 million, and then we're going to estimate the weights in order to, just to introduce, I'm going to use inverse probability weighting to check that the model is correct. So first I need to get the weights by fitting a generalized linear model, a logistic regression for B given A and Z. Okay, so that's what we do first. And then we use 1 over the probability of you observing the value of B that you actually get as our inverse weight. And what we find is that the bias in the linear model is very small. So this is the model for Y given do A and B. And the true values, remember, were -1 for the intercept, a half for each of A and B, and 0 for the interaction. And you can see our estimates are very close to those values. And you can kind of do a bit more. So you can look at the, you can look at the Z value, and this is the difference between these two guys divided by the standard error. And you can then do a hypothesis test to see whether that's significantly different from the value that it's supposed to be. And you can see that you wouldn't reject any of those hypotheses. So this suggests that our simulation method works very well. And you can do this, say, 1,000 times. Instead of having 10 to the 6 data, reduce it to 1,000 and do it 1,000 times and look at the bias in these estimates. And you can see that this is bias 0, so it's actually a very, very good fit. So this suggests that our simulation method is working very, very well. And for comparison, we can look at a naive model where we just regress Y on A and B, and you'll see we now do have bias. So the intercept has shifted significantly down, and the coefficient for B has gone up a lot. Okay, so sort of main message I'd like to get across in this talk is that causal models are marginal models, right? So if you want to do causal modeling, it's helpful to know about marginal models and methods for dealing with them. And what I'm sort of hoping is that this work will inspire people to go and look at the marginal modeling literature, which is very large and has lots of things in it that people might not have thought to apply to causal models before. So I've shown you marginal structural models, but we can also apply it to lots of other kinds of models. So survival models, dynamic treatment regimes, structural nested models, and you can also enforce things like stationarity and transportability by using these parameters. Sort of slightly different causal tack, you can also simulate from arbitrary instrumental variables models using this method as well. So you just specify what the causal relationship you want is, and then build up the rest of the model around it, and you simulate using a Copula or whatever it is that you, whatever method it is that you want to use. So I didn't explicitly show this, but you can just, so instead of using the inverse probability weighting, I could have fitted the model because we can evaluate the likelihood. And actually that works very well as well. So I don't have a plot for it, but you find that if you use the maximum likelihood estimation, you get essentially the same results as you get from inverse probability weighting, which in turn shows that inverse probability weighting is actually a very good method to use because you're getting almost as good as MLE, but it's much, much faster. You only have to use ordinary generalized linear models. So the limitation, I guess, is that actually the simulation is inefficient in higher dimensions. So because we have to use rejection sampling, that becomes very inefficient. So you just reject almost all the samples if the samples, if the XZ space becomes very large, basically. So we're working on other methods to try and make that more efficient. Thanks very much. So we have a paper that I just released on arXiv this week. So please do go and check it out. Thank you.
Thank you. Very, very, very interesting and thought-provoking with the IV angle as well. I have one quick question that I will shoot out, but the rest can then just think about if there are further questions. It seemed to me that there were elements of this which was well, not generic, but sort of some of the overhead, some of the structure for the coding would be the same irrespectively of the exact, like for the IV or for the survival or something like that. So how are you in terms of software? Some of this sort of partly implemented, and then you can plug your own component where you need to change, or you have to start from scratch?
Yeah, so it's a good question. I didn't have time to point this out, but there is an R package on my GitHub. So I can type it in the chat if I should have put it on a slide. Yeah. So if you go to RJE42/causal. Oh no, sorry, that's the wrong. It's supposed to be saying to everyone.
Maybe just throw it in the chat. So,
can you see that?
Oh, perfect. It's there. Yeah, perfect.
So if you go to that GitHub repository, then there is a package which will do this. It's a bit limited at the moment, but yeah, you're right. So it should be relatively straightforward to extend it to other kinds of models. So the main thing we've got is basically a method of simulating from copulas, and then you just transform the density. You just transform the margins at the moment. So I'm hoping to add in the discrete stuff. At the moment, it's a bit of a mess, so I don't want to publish it. But yeah, so yes, you're right. Okay. It should be quite straightforward to apply it to other things.
I have one more, but are there other questions? This was just for the inefficiency. I was thinking a little bit like along the lines of you saying we have to remember what there is with all the work already done on marginal models, and simulating from complex high-dimensional distributions is difficult, but it is certainly something people have been looking about a lot. Bayesian people, there are a lot of people who've been thinking about those lines. Do you feel you have explored if this is a problem that has been tackled elsewhere, or? Yeah,
so my colleague Arnaud Dusay, of course, is very much into simulating high dimensions, and we're going to have a chat about a method he's spotted which he thinks would make this very easy. So we'll see whether that works.
Okay, thank you. We are at the slightly delayed, but otherwise on time. So please join me in I hope you know what I meant. Please join me in thanking Robin once more. And then Linbo Wang said that his speaker's situation should hopefully have been resolved. So, as I said before, Linbo Wang from the University of Toronto, who will talk about causal inference on distribution functions. So, the floor is yours.
Okay, is this better or no?
It is amazingly much better. So if now
okay.
You can just show.
I think the only difference is I log into Zoom this time. So previously I just logged in as a guest. I think that makes a whole difference. But anyway, apologies for the audio problems, and